Okay, so for 2.4 we're going to consider the following library of what are called parent functions. So they're kind of more basic functions that aren't too crazy. An example of a non-parent function would be something like f of x is equal to x squared minus 3x plus 2. We'll see this in the next section, but this, as it turns out, is what is called the transformation of a parent function. And the highest power is 2, so it's actually a transformation of x squared. I also said that any quadratic function has a graph that's a parabola, and both of these are parabolas, and in fact if you do something to this parabola you'll get the graph of this function, so it's kind of interesting. But really 2.4 is about laying down the groundwork as far as the fundamentals go. So here are the fundamental functions. So the first one is the constant function, f of x is equal to some constant. It's just a horizontal line. This is what is known as the identity function, f of x is equal to x. So when you plug in a number, you get back the same number. But it's just a line. Slope is 1 over 1, has a y-intercept of 0. Here, this is x squared, which is just the, I guess, parabola centered at 0, 0. Here, this is x cubed. It looks kind of similar to x squared, only the left half is down instead of up. It's actually supposed to be a little skinnier, too. So it increases way more quickly than x squared does, which I think is obvious when you plug in numbers, like plug in 2, 2 squared is 4. When you plug in 2 here, you get 8, which is way, way taller than 4. Here, this is the square root function, which does exactly what the parabola function does, but it's just rotated basically, and only the upper half. The reason why it's only the upper half is because, remember, when you square root both sides of an equality, of an equation, you get a plus or minus. So again, we'll see more of this in the next section maybe, but the positive case is here, and the negative case would be down here. So if you wanted to complete the parabola to get the lower half, this would be f of x equals negative radical x. But more about that in the next section. In fact, we'll see that phenomenon play a role in later sections as well. But and then f of x equals x cubed is also just a rotation of x cubed. 1 over x is the reciprocal function. It's kind of a weird one. It looks similar to something we saw in the last section. There is what is called a vertical asymptote. There's also a horizontal asymptote at the x and y axis. The absolute value function we actually haven't seen. We've talked about absolute value, but we haven't seen the graph of the function, which is interesting. Now, the cool thing about this graph is that it can be written as the following. Well, the function anyways can be written as the following. So what you can say is that f of x is equal to one of two things. Either it's x over here, and this happens when x is bigger than or equal to 0. Okay. Otherwise, when x is less than 0, this part of the function is negative x. So if you were to graph y equals x and y equals negative x, you'll get this line in its entirety and this line in its entirety. But if you only want to keep x when x is bigger than or equal to 0, you'll be looking at this right half, and then similarly when x is less than 0, for negative x, it's going to be only the left half. This is what is called a piecewise-defined function. We'll see that a little more right now, but I at least wanted to start off with a nice transition into that, and we'll see examples of that right now, as well as the definition for what piecewise-defined really means. Let's see that right now. Okay, so here I say a piecewise-defined function is one of the form f of x is equal to g of x, h of x, or any other function. There could be multiple of them. The last example we saw was only 2. There could be 3. Mainly it'll be 2 for this section we'll be looking at, but you could have multiple, which is why I wrote the dot, dot, dot. And then here these are the restrictions. So here these are the functions that you'll get. Whereas over here we have the restrictions as far as when we have those functions. So there's a kind of comma separating the function from its restriction when it occurs. So let's consider this example, f of x is equal to x squared when x is less than 1, less than or equal to 1, and x when x is greater than 1. So I'm going to show you the graph first off. So let me just graph each of these. So I'm going to graph x, and I'm going to graph x squared. So x, f of x equals x looks like that, remember that. And f of x equals x squared looks something like this. I think that looks okay. Now what? Well, this whole thing is not a function. It fails a vertical line test basically everywhere. But luckily for us, there's this, I guess, separating term 1. So the restriction is when it's less than or equal to 1, so let me graph 1 here, or plot 1. By the way, that's where they intersect as it turns out. 1 squared is 1, and 1 is also 1. But yes, when it comes to x being less than or equal to 1, so on the left, when x is less than or equal to 1, we want to only work with x squared. So on the left, I'm going to erase everything except for the parabola. Just like that. Okay, very similarly on the right, what happens? Well, on the right, when x is bigger than 1, we only want x. So we're going to erase the parabola and only keep the line. So this is a weird function, or weird graph, but this is what f is. It's kind of a Frankenstein, if you will, of different functions, just kind of glued together as needed. And that's what a piecewise-defined function really is. So we'll take a look at one more example of this. And in this case, these are linear. These are both linear functions, which we can graph using slope-intercept form. So I'll do that. So let's see, x plus 6, we'll start at y equals 6. 1, 2, 3, 4, 5, 6. And it has a slope of 1 over 1, but remember that its 0 is negative 6. When you plug a negative 6, you get 0. So I'm going to actually just do that. So all I'm doing is plotting the x and y intercepts, and then creating from those 2 points the line, which is the graph of that function. Let me make that a little better. There we go. That looks nice. Good. So now what about the other one? Well, the other one is 1/2 x minus 4, which has a y-intercept of negative 4. And if you want to find its 0, well, when x is equal to 8, when x is equal to 8, actually, we get 4 minus 4, because half of 8 is 4. So its x value is actually going to be positive 8, which is way over here. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. This was negative 6. This is positive 6. So connecting these two, we get this line. Now, these lines both have different slopes, so as it turns out, they will intersect eventually. I'm not going to find out where they intersect, because that's not really of interest to me. What is of interest to me, though, is which ones to erase. Where do I erase each of them? Let's take a look. So it has to do with x equals negative 4. So let's go to negative 4 and plot the point for each of those. And where do we keep them? Well, the first one is only alive when x is less than or equal to negative 4. So I'm going to erase it on the other side. So I'm erasing it here when x is bigger than negative 4. Because we only want it to be true when x is less than negative 4 or equal to negative 4. Similarly, we don't want this line to exist over there, or else we don't have a function because it will fail the vertical line test. So this is it. These two lines, it's not a continuous function. I haven't even discussed continuous, but basically it means that there's a break somewhere. So there's a jump from one to another, which can happen. It didn't happen for this one, so it could have, because this line could have been a little above or a little below, but it was exact in the sense that they both connected at that point. Here, that didn't happen. That's a possibility for piecewise-defined functions. But anyways, it's how you graph piecewise-defined functions. You just graph each part of them and only keep the part for its corresponding restriction. And that's basically it. So that's basically it for chapter 2.4. In the next section for 2.5, we'll discuss transformations, where it gets a little more interesting, and we'll utilize a lot of our knowledge on parent functions, and we'll see that in the next video. See you then. Thanks for watching.